Hello everyone and welcome to ETAP Digital Innovation Day, Transmission, Distribution and Microgrid. My name is Aslan Mojallal and today I will be presenting ETAP Power Plant Control Solution. During this presentation, first I will talk about some of the key features of ETAP for simulation and analysis. Then I will briefly talk about Power Plant Controller, what it is and when and why to use it. And after that, I will talk about ETAP PPC solution. Then I will use ETAP PPC and run some study cases that I have prepared for this presentation. And finally, I will perform a hardware in the loop or HIL test to demonstrate the capabilities of ETAP PPC. From the simulation perspective, it is well known that ETAP can perform load flow, short circuit, and harmonic analysis, and it has all of the elements that are needed for modeling a renewable power plant. For example, in this power plant model that I have here, if I go to the PV element, settings related to an individual PV panel, an array of PVs, and the inverter that PV panel is using can be entered through the editor of PV element. We can also take a look at a WTG element, for example, and you can see that we can enter the settings for various aspects of operation of this WTG element. For example, the rating of the WTG or the short circuit model of the WTG and so on and so forth. When it comes to a renewable power plant, we want to be able to take a look at the behavior of the system over a long period of time. And for that purpose, ETAP offers time domain load flow module. And from here, we can see that we can run the renewable power plant for a long period of time and study its behavior. In time domain load flow, we can use external data to take into consideration the fluctuating nature of our renewable assets. We can also use the profile library for our renewable sources, for example, the PV irradiance or the wind speed, to accurately model the behavior of these assets over a long period of time. For a renewable power plant, when we are using the time domain load flow, most of the time there are controller actions. And for that purpose, ETAP offers quasi-dynamic load flow to consider the operation of the controllers within the simulation environment. And some of the benefits that quasi-dynamic load flow offers are that it enables the design and feasibility studies, investigating the grid code capability of a renewable power plant, sizing energy storage and renewable assets in a system, and figuring out and tuning the optimal power plant control settings. Also, ETAP offers transient stability module, which is essential when we want to investigate the stability when there is one or several controllers in the system, or when we want to study the write-through capability of our assets and their compliance with the grid code. Now let's see what a power plant controller is. When it comes to interfacing a large renewable power plant with the utility, the operator mandates certain requirements at the point of interconnection. For this purpose, we use a controller called a power plant controller that is responsible for coordinating and dispatching active and reactive power within the plant to meet those requirements. So PPC receives the operator commands as well as the measurement coming from the power plant, and then dispatches assets within the power plant to satisfy the operator commands. Now let's take a look at ETAP PPC solution. As you can see here, ETAP PPC communicates with different assets within the system, for example, PVs, WTGs, and energy storages, and so on. And as part of ETAP PPC solution, we have ETAP real-time server that is used for monitoring and archiving the data. ETAP SCADA and HMI is another piece of ETAP PPC solution that is used to monitor and visualize the data for the entire system. When it comes to large and specifically hybrid power plants, because of the reliability and communication issues, the entire power plant is divided into several sub-power plants, and each of these subsystems have their own power plant controller. And then one master PPC is used to coordinate these sub-PPCs. Now let's take a look at some of the key and unique features of ETAP Power Plant Controller. First of all, ETAP Power Plant Controller is model-driven, and this means that ePPC has access to the settings of all of the elements that it is monitoring or controlling. And this is a really big advantage because it offers simplicity and flexibility when we are designing the control system and when we are setting it up, as well as when the controller is in the operation. The next key feature of ETAP PPC is that it is a software-based controller. And this allows us to define advanced functions for this controller, and it significantly reduces the testing that is required for validating it. Also, since this controller and the renewable power plant model is available in ETAP, we have an identical digital twin of the system. And this allows us to perform testing, validating, and modifying the logic of the controller very simply and effectively. Finally, ETAP Power Plant Controller is cross-platform, which means that it runs on Microsoft Windows and Linux Red Hat. The next important thing to discuss is the built-in functions of ETAP PPC. The power plant controller that ETAP offers has active power control, reactive power control, and renewable smoothing functionalities built within it. For the active power control, the power at the point of measurement is regulated, and this functionality can have a rate limiter and a pH droop control. For the reactive power loop, reactive power voltage or power factor at the point of measurement can be regulated. And again, this functionality can have a rate limiter and a QV droop control scheme. And also the PQ capability of all of the sources are taken into consideration when PPC is dispatching them. Okay, now that we have covered the basics of ETAP PPC solution, let's take a look at an example PPC and run some study cases. Here is a hybrid renewable power plant composed of a PV plant, a BESS system, a STATCOM, and a WTG farm. And here is the power plant controller that is coordinating and dispatching assets within this renewable power plant. Now, one important thing that I want to mention is that this PPC in ETAP is the identical digital twin of the power plant controller that goes into the hardware. So it has the exact same logic and behavior as the hardware PPC. And as you can imagine, this configuration of having an identical digital twin of this controller in the software and in the hardware makes testing, validating, and commissioning this controller extremely simple and efficient. If I open this power plant controllers editor, under the DLL tab, we can see the settings for this controller element. Under the device setting, we determine whether or not this PPC is enabled or disabled. What is the type of PPC? For example, is it a master or a server PPC? And also how often this controller is executed and so on. Under the system setting, we familiarize the controller with the power plant. For example, we determine what is the plant side bus, utility side bus, what is the meter at the point of measurement, and so on. We also define the PQ capability of the assets within this renewable power plant for PPC to consider them in the reactive power control loop. And also keep in mind that because controller element in ETAP is model driven, once we familiarize PPC with an element, it automatically gains access to the settings of that element. And as you can imagine, this makes setting up this controller very simple. The next setting is the general setting where we define the ratings of the power plant for the PPC. These settings are used for internal calculations of PPC, as well as converting the settings in the active, reactive power control loops and also renewable smoothing settings that we will get into. The next item is active power control, where we define the settings that this PPC uses to regulate active power control at the point of measurement. And also, this is where we define whether or not we are using a ramp rate limiter and what is the value of that ramp rate limit. As you can see, the unit of this ramp rate limiter is percentage per minute, which is based on the rating that we have defined in the general setting. We can also define a dispatch priority for PPC to use assets subsequently, one after another, or dispatches them automatically based on the ratings of assets all at the same time. Next, we can define the proportional gain and integral gain of the internal PI controller that this PPC uses. And finally, we can enter the settings for p-Hertz droop control that this controller uses to adjust its active power because of some fluctuations in the frequency. The settings for reactive power control is similar to the settings for active power control, but here in addition to reactive power control, we can control voltage or power factor. And also in the dispatch priority, we determine what are the assets that are contributing in reactive power control and what are the priority of their usage. And instead of a p-Hertz droop curve, we have a QV droop control scheme. The next item is the settings for renewable smoothing functionality. And here we can choose from the 3 different types of internal logic for renewable smoothing. And then we can enter the settings for each of these functionalities individually within their own section. The communication setting is reserved for when this controller is placed in a hardware and it is communicating with either ETAP as real-time simulator or with the actual data coming from the field. Okay, now that we have covered the settings of power plant controller, I'm going to run a scenario that PPC controls the active power at the point of measurement according to some commands that are coming from the operator of the system. Here I have scheduled some commands from the operator. At 10 seconds of simulation, an active power command equal to 15 megawatt is sent to PPC, and at the second minute of the simulation, the active command is changed to 25 megawatts. And if you recall from the presentation, I'm going to use time domain load flow with quasi-dynamic model enabled because we have control actions within this simulation. And I'm going to run this simulation for 4 minutes with time step of 100 milliseconds. Okay, let me run this case. I skipped to the end of simulation to save some time. And now let's take a look at the active power at the point of measurement. Here we can see at the 10 seconds of the simulation, PPC receives a command from the operator of the system to reduce its power to 15 megawatt. And it dispatches the assets within the system to reach to this goal. If I go back to ETAP, we can see that the rate limiter is 50% per minute and the rating of the system is 36 megawatt. So we expect to reach from the initial point of 29 megawatt to 15 megawatt within around 46 seconds. And this is basically what happens, and we can confirm that the rate limiter is limiting the rate of change of power at the point of measurement according to its setting. And also at the second minute of the simulation, a command is received by the PPC to increase its power to 25 megawatt. And from this figure, we can see that the PPC dispatches asset to increase the power of the plant to 25 megawatts. Now, if I come back to the power plant controller and take a look at the dispatch priority, we can see that we wanted PPC to first dispatch our PV system. And if PV plant doesn't have enough power, then we wanted PPC to generate power from WTG to meet the command. So let's take a look at the active power of the PV plant and WTG farm. Here we can see the power plant controller uses PV as much as possible, this blue curve. And if it needs to curtail a source to meet the command of the operator, it uses the WTG farm because it has the second priority. Okay, now let's run a scenario where PPC regulates the reactive power at the point of measurement. For this purpose, I have scheduled the command from the operator of the system to send the command at the 10 seconds of the simulation equal to 4 megawatt of reactive power. And at the second minute of the simulation, the reactive power command is increased to 12 megawatt. We also have a ramp rate limiter in the PPC equal to 50% per minute. And we have a dispatch priority for PPC to first dispatch a STATCOM, then PV plant, and finally WTG farm. Okay, I am going to run this scenario now, and I will show you the results once the simulation is finished. All right, let me plot the results. From this curve, we can see that starting from 10 seconds, Power plant controller dispatches the assets within the system to increase the reactive power of the plant to 4 megawatt. And at the second minute of the simulation, it increases the reactive power of the plant to 12 megawatt. And for both of these operations, it is using the ramp rate limiter that we have defined for it. Now let me plot the reactive power of a STATCOM, PV plant, and WTG farm that are contributing in reactive power control of the plant. Taking a look at this curve, we can see that PPC first uses a STATCOM, or this orange curve, because it has the highest priority. And once a STATCOM reaches its maximum value, it starts to use the second priority for reactive power control, which is the PV plant, or this blue curve. And finally, once PV plant reaches its maximum reactive power capability, it dispatches the wind farm as the lowest priority for reactive power control. So PPC uses these three assets to regulate the reactive power at the point of measurement intelligently. One thing that I need to add here is that the PPC is capable of controlling the active and reactive power simultaneously. But I use these functions individually for the purpose of presentation. Now that we looked at the active and reactive power capabilities of the power plant controller, let's perform a hardware in the loop test. For the hardware in the loop test, I'm going to use ETAP as the real-time simulator of the power plant. And I'm going to use the communication protocols to send the measurements calculated by ETAP as simulator to the hardware PPC that will contain the exact logic that I just showed you. And then I'm going to use web client to show the real-time results coming from the simulator. It is very important to note that how easy and effective this process is and how much time and resources it will save to test and validate the entire process. Okay, let me come back to the power plant controller in ETAP, and in the communication settings, I need to enter the details for communicating with the hardware. I have already entered these settings, so the next step that I need to do is to deploy the controller. And deploying this controller gives me a file that contains the exact same logic of the PPC that I ran in the simulation. And we can see it here. Okay, so far I have deployed the logic that will be uploaded in the hardware, and I have set up the ETAP real-time power plant simulator. Now let's take a look at the web client. Here is the web client that we have for ETAP PPC hardware. And I can upload the logic that I just deployed here. Now this controller contains exactly the same logic that I used to run the simulation cases. All right, now everything is set up. ETAP will run as real-time simulator of the power plant. We have uploaded the logic within the hardware, and we can perform the HIL test. So let me run ETAP. So if I go to the power plant page of the web client, here we can see that the power plant controller is enabled, so it is controlling the active and reactive power. We can see the mode of operation of the power plant controller, the grid's voltage, frequency, and its status, as well as the power factor at the point of measurement. And in the real time, we can see the active power, reactive power, and voltage. Right now, because I just performed the test, these curves are empty, but they will be populated over time. Through the web client, we can see the measurement for other assets within the elements as well. And we can take a look at their values in real time. Okay, now that the HIL test has finished, we can still look at the curves within ETAP because we were using ETAP as real-time simulator. So let me plot the active and reactive power at the point of measurement for this test. So if we take a look at the active and reactive power commands, we can see that the power plant controller is dispatching assets to meet the reference values that are being sent by the operator of the plant. So here I want to make the conclusion that doing HIL testing with ETAP power plant controller is fairly straightforward and simple. And with that, I want to conclude this presentation. Thank you everyone and have a good day.